All right, so we're going to look at calculating the standard cell potential for the reaction as written. Notice I've filled in my oxidation numbers, and so that means then that if silver is going from +1 to 0, it is being reduced. If zinc is going from 0 to +2, it's being oxidized, and so that's a pretty important first step to establish what's being oxidized and what's being reduced. We've talked about defining which substance is doing what at the anode and the cathode, and we know that the saying we go by is an-ox red cat, so that means that the anode is going to be zinc, so I'll just write that down here. So anode is zinc, and the cathode is then going to be silver. And so again, this is going to be the oxidation, and this is going to be the reduction. So when I go to find the cell potential, I am looking up, again, this is the standard cell potential, so I'm going into that chart that was given. And so these are reduction potentials. So that means that this is written from the perspective of reduction reactions. So you'll notice that what's happening to the silver, which is being reduced, so it's going from +1 to 0, so going from +1 to its elemental form. I'll actually find that format on here. So I need to look down the list until I find silver. And where are you, silver? Here it is, right here. So this silver gaining an electron, this is showing reduction. So this is the voltage for that reduction compared to the standard She electrode. So 0.80 V for that. So I'm going to write that there. And so basically, just to review what we talked about, the reduction potential for the cell, or the cell potential, is the reduction potential. So you might either see this written as red, or you might either also see it written as cathode for the cathode, whichever species of the cathode. And that's going to be, again, a couple different ways you might see this written. This is plus the oxidation potential. Again, this is what's occurring at the anode. The thing we need to be careful about is the potential for the oxidation. Since all of these values are given to us for reductions, basically oxidation will be the reverse of what's given on this sheet. So you have a couple choices. You can, again, figure out what's being oxidized, and then, again, we're talking about the reverse reaction, so we'd be changing the sign of the standard potential for that particular reaction. Or another way that you might see this written out sometimes is we'll have the reduction, and then minus the, and sorry, this is at the cathode, minus the number from the anode. So that way you don't have to worry about switching the signs, and you just consistently, if I'm subtracting off the value that's given on the sheet, then I'm basically changing the sign and accomplishing what I just talked about up here. So again, I'm going to look up the reaction for zinc. Again, we need to be careful because some of these substances, not these, but some substances can gain or lose different numbers of electrons. So this is zinc +2 and silver +1, and so we find zinc on the sheet, and so this is -0.76. So again, changing the sign of that, if that's the oxidation potential. So I'm adding the two together, 0.80 plus 0.76, and that gives me 1.56 volts for the potential for the cell. And again, that's the standard potential, so that means standard conditions, 25 degrees Celsius, and concentrations of the solutions at 1 molar. And again, this is going to be independent of the coefficients in the balanced equation, so I don't need to factor in the fact that the silver has a 2 in front of it, and that will always be the case because this is an intensive property, the voltage. Because again, we'll talk about this unit in class, but volts is defined as joules per coulomb. And so, if I am transmitting more, if I've got more species represented in the reaction, there'd be more energy transmitted, but there would also be, or more energy exchanged, or whatever, however you want to say it, but there'd also be a greater charge flow as well. So that ratio will remain the same, and we don't need to adjust for coefficients.